So certain remarks can be made out of the cut set matrix CG. So those are as follows. As in the case of incidence matrix, a permutation of rows or columns in a cut set matrix corresponds simply to renaming of cut sets and edges. So just like the way we saw it in the incidence matrix, a permutation of rows or columns, like replacing the rows and columns among themselves, would simply result in something that would seem like as if we have renamed the cut set and the edges. The second one is each row in CG is a cut set vector. So as you can see, like each row in CG is a cut set vector. A column with all zeros corresponding to an edge forming a self loop. Now, in our example, we don't have a column where with all the zeros, but like for instance, let's assume like if there was a let's assume there was a self loop over here. So if there was a self loop over here, then a cut set, then a cut would wouldn't change the vector, won't change the vertex in any way, won't affect the vertex in any way. So there would be a zero over here, right? So that explains. The next one is parallel edges produce identical columns in a cut set matrix. So in this particular example, A and B are the parallel edges, and the as you can see, the A and B are identical, like they are totally identical to each other. The next point is in a non-separable graph, every set of edges incident on a vertex is a cut set. Therefore, every row of incident matrix AG is included as a row in the cut set matrix CG. In other words, for a non-separable graph G, CG contains AG. For a separable graph, the incidence matrix of each block is contained in the cut set matrix. So it states that in a non-separable graph, every set of edge incident on a vertex is a cut set. So what is a non-separable graph? Non-separable graph is basically a graph where the vertex connectivity is not 1. So for example, this graph. So if I were to remove this edge, this vertex, then this and this edge would go, but it won't be a disconnected graph, right? But if I were to remove this vertex also, then these two edges will also go, these two edges will also go, so it would become a disconnected graph. So this is an example of non-separable graph. So let's find the uh, incidence matrix and cut set matrix of this graph. Okay, so let's for the edge one, for the vertex one, it would be like uh, E1 and E4, and for the second one it would be E1 and E2, so E1 and E2. For the third one it would be E2 and E3, so E2 and E3. For the fourth one it would be E3 and E4, so E3 and E4. For the cut set, let's assume there's a cut like this, and third cut is this one, and fourth cut is this one. So for the first one, it cuts E1 and E4, so E1 and E4, and the second one cuts E1 and E2, so E1 and E2, and the next one is E2 and E3, so E2 and E3, and the fourth one is E3 and E4. So as stated, every row of incidence matrix AG is included as a row in the cut set matrix CG. So every row of incident matrix is included in the cut set matrix. As you can see, like 1001, same, it's like the same. Every row is included in the cut set matrix. Okay, so basically CG contains AG, right? So from this observation, we can make out that rank of CG will be greater than or equal to rank of AG, right? And we have already found out, like there's a proof for this, the rank of AG. So we know the rank of AG is n minus 1. When we substitute its value, we get that rank of CG is greater than equal to n minus 1. This is our theorem number 7.6. This is our equation 7.6. So so the next conclusion, next conclusion from that matrix is, since the number of edges common to a cut set and a circuit is always even, every row in C is orthogonal to every row in B, provided the edges in both B and C are arranged in the same order. In our case, we have arranged the edges of B and C in the same order. Okay, so they are orthogonal. So therefore, every row in C is orthogonal to every row in B. Therefore, by mod 2 arithmetics, we know that B dot C transpose is equal to C dot B transpose, which is equal to 0. When we apply the Sylvester's theorem to this equation, we get rank of B plus rank of C is less than equal to E. Now we know the rank of B, that is the rank of a circuit matrix, is E minus n plus 1. Now when I substitute the value of rank of B in this equation, I get that rank of C is less than equal to n minus 1. Now from the equation 7.6 and 7.7, so 7.6 and this equation, I get that rank of C is equal to n minus 1. So therefore we derive a theorem that the rank of cut set matrix CG is equal to the rank of incidence matrix, which is equal to the rank of graph G. Like as you can see, that rank of this is n minus 1. Rank of incidence matrix, or like we have already proved for that, that's n minus 1, and the rank of the graph is also n minus 1. So therefore, the theorem that rank of cut set matrix CG is equal to the rank of incidence matrix AG, which equals to rank of graph G. Okay, so now I'm going to explain fundamental cut set matrix CF. This matrix is an n-1 by E submatrix such that rows correspond to set of fundamental cut sets, columns correspond to n-1 branches and E minus n plus 1 chords. A fundamental cut set matrix CF can also be partitioned into two submatrices, that is identity matrix IN-1, which is of order n-1, and CC submatrix, which corresponds to the chords. And the fundamental cut set matrix CF can be written in this format, that is CF is equal to CC IN minus 1. Now I'm going to explain all these points with the help of an example. So this is the graph. So the first step to get a fundamental cut set matrix is we need to convert this graph into a spanning tree. So I have like this is the spanning tree of that particular graph. So here the edges H, E, G, F, A are the branches of the spanning tree, and the edges B, C, D are the chords of the spanning tree. So here it's written that columns correspond to n-1 branches and E minus n plus 1 chords. So what I have done is that I have first written down the chords, and after that I have written down the branches, right? So for this spanning tree the chords were B, C and D. So I have first written down the chords, and after that I have written down the branches A, E, F, G, H. Like, and to get the rows, just like we did it with the cut, to get the cut set matrix, we need to put cuts. So okay, if I put a cut over here, it passes through the edges A and B. So I put a 1 in B and A. If I put a cut over here, it passes through the edges E and C. So C, E. If I put a cut over here, it passes through the edges F and D. So D, F. If I put a cut over here, it passes through the edges D and C and G. So C, D and G. And if I put a cut over here, it passes through the edge H. So that way I get the fundamental cut set matrix. So rows correspond to set of fundamental cut set matrix. So these are the rows. I've explained how we got the rows, and then the second point also I've explained. Yeah, so cut set, it's basically partitioned into two submatrices, right? So CC, which corresponds to the chords, and IN minus 1. So this one corresponds, these are two submatrices. This one is for the chords and this one is for the branches. So CC represents the chords. Yeah, so BCD are the chords. So that's how we got the submatrix CC. And the other one is of the form IN minus 1, where n represents the number of vertices. Okay, so in this particular spanning tree, we have 6 vertices. So n minus 1 will give us 5. So there are 5, though. So it's an identity matrix of order 5. So that's how we got the fundamental cut set matrix. So in this video, I'm going to explain the relationships among AF, BF, and CF, where AF stands for reduced incidence matrix, BF stands for fundamental circuit matrix, CF stands for fundamental cut set matrix. So this is the graph. I have made the spanning tree for the same graph, and here the edges H, E, A, G, F are the branches of the spanning tree, and the edges B, C, D are the chords of the spanning tree. This is the incidence matrix. Now, how to write this incidence matrix has already been explained by Evan, so I'm not going to get into that. We'll move to reduce incidence matrix. So to write the reduce incidence matrix, you just have to remove one of the rows from the incidence matrix. And in this case, I have removed the last row. And as you can see, AF has basically two submatrices, AC and AT, where T stands for the submatrix of the branches of the spanning tree, and C stands for the submatrix of the chords in the spanning tree. So basically we have to reorder the columns. So first we have to write the chords. So in this it's BCD. So first I have written down the chords, and after that I have written down the branches of the spanning tree. The branches A, E, G, F, H. So that's how I got the AF. After that, BF, the fundamental circuit matrix. Now, how to write the fundamental circuit matrix has already been explained by Joyce. Next is CF, fundamental cut set matrix. I have already explained how to write this fundamental cut set matrix. Now, as we know, AF is equal to ACAT, BF is equal to I mu BT, CF is equal to CCIN minus 1. Where T denotes the submatrix corresponding to the branches in T, C denotes the submatrix corresponding to the chord, and in this I mu, I stands for identity matrix of order mu, and IN minus 1 stands for identity matrix of order n minus 1. One thing to be taken into account is that for all these three matrices, the order of the edges is same. That is B, C, D, A, E, F, G, H, B, C, D, A, E. As you can see, the order is the same for all of them, and it's the same edges, same columns in all the three matrices. So since the column of AF and BF are the same, we can apply this particular property. The property is A dot B transpose is equal to B dot A transpose is equal to 0. So when we apply it to the matrices, the reduced incidence matrix and fundamental circuit matrix, we get that AF dot BF transpose is equal to 0. So in this one, when we substitute the value of AF and BF from equation 1 and 2 in this, if in this particular equation we get ACAT dot I mu BT transpose. Now when I take this transpose inside, I get this. Now the dot product of these two will get me AC plus AT dot BT transpose. Now, as we know, AT is non-singular, so there has to be an inverse. So I can say that AT inverse exists. Now, multiplying AT inverse to this equation. This is from the same slide, so just ignore this for now, for the time being. So multiplying AT inverse to both the sides will give us AT inverse dot AC is equal to minus BT transpose. Now from mod to arithmetics, we know that minus 1 is equal to 1. So by applying that, I get BT transpose is equal to AT inverse dot AC. This is our equation number 4. Now I apply the same thing for BF and CF, that is for fundamental circuit matrix and fundamental cut set matrix, and I get CF dot BF transpose equal to 0. just like the previous, like similarly. And here also substituting the value, like substituting the value of BF and CF, I get this. And then again, when I apply this by mod 2, I know that -1 is equal to 1. Therefore, I get CC is equal to BT transpose. So this is our equation number 5. Now from equation 4 and 5, we get that AT inverse dot AC is equal to BT transpose, which is equal to C. Okay, so from this, we can draw certain conclusions. The conclusions are, the first one is, given A or AF, we can readily construct BF and CF, starting from an arbitrary spanning tree and its subgraph AT in AF. So from a given A or AF, we can readily construct a BF and CF. So suppose you're given AF. So if you are given AF, you have AC and then you have T inverse also. So if you have if you have AF or A, you can easily construct the BF or CF, right? So from this, this is the first conclusion, and the second one is, given either BF or CF, we can construct the other. Thus, since BF determines a graph within two isomorphisms, so does CF. So given either BF or CF, we can construct the other one. So if you're given BF, if you're given BF, so you have this, like BF is equal to I mu BT. So if you're given BF, you have this, and therefore you will get the value of CC. Now when you put the value of CC, you just need to add the identity matrix for the n minus 1, and then you'll get the CF. So it goes vice versa also. If you have CF, then you have CC, then you will derive, from there you'll get the value of BT transpose, and from there you'll get the value of BT, and then you can get BF. So if you have BF or CF, you can construct the other one. And the final conclusion is, given either BF or CF, AF in general cannot be determined completely. So as you can see, if you're given a BF or CF, you can't determine AF, because AF is, as you can see, it's a product of AT inverse dot AC. Therefore, it cannot be completely determined. So this is the third conclusion. Yes, that's it.